So this chapter is about work and energy. And conservation of energy. So in physics, work is defined as there is a way to calculate the amount of work done, and that is force times distance. So if you apply force to an object and you move it through some distance, then you have done work. And the amount of work done is measured, is calculated by this formula. Work is equal to force times distance, and the unit of work is joules. Okay, the force is measured in newtons, and the distance is measured in meters. So technically, when you will multiply those two things, suppose there's 5 newtons and 2 meters, then 5 newtons times 2 meters will be 10 Newton meter. But instead of writing Newton meter, you will write joules. Newton meter becomes joules. Okay. Then comes energy. Energy is actually very similar to work in terms of physics. So energy is the capacity to do work. It is also measured in joules. So in everyday life, maybe we think of work and energy as different things, and in physics also they are different, but in also many ways they are quite similar. So many times you will find the equations of work and energy to be very similar. So energy is the capacity to do work. Now talking about work, suppose you have a block to which you are applying a force of 6 newtons, and by applying a force of 6 newtons, you move it through 5 meters. Then 6 times 5 is 30. So 30 Newton meters or 30 joules is the amount of work done. However, there's another thing about work, which is that the displacement should be, so I kind of, I guess I just more casually use the word distance, but this should be displacement. Okay. So remember the difference between distance and displacement. This is A, this is B. The total length along this curved path is the distance, but the straight line path between the initial position and final position is the displacement. This is displacement. Okay. Is that sound coming from your computer, the chat or email sound?
I don't think so, no, because I don't have any like emails popping up or anything.
Okay. All right, that must be my computer. That's okay. Yeah. So when calculating work, the force that we consider should be in the direction of the displacement. So suppose you are dragging luggage at the airport, right? And you are applying the force in this direction, and it is also 6 newtons, and also you go 5 meters. But this is not, exactly in the same direction as the displacement. So let's say this is 30 degrees. Actually, let's make it 60 degrees. So you have to split up this force into horizontal and vertical direction. So this one will be 6 cosine 60. And the vertical portion will be 6 sine 60, but we are not worried about that. We are only worried about this one because this is the component which is in the direction of the motion. So we will do 6 cosine 60. And I intentionally chose the angle 60 because cosine 60 is half. Okay, so it's an easy calculation. So 6 cosine 60 will be 3 times 5, 15 joules. So 15 joules of work will be done in this case. All right. So when you are applying a force, all of that force may not be used up to do work. It depends on the angle. So a more general equation of work is work is equal to F d cosine theta, where theta is the angle between force and the direction of force and the direction of displacement. Okay. Now, the interesting thing about work in physics is that sometimes you could have zero work, even though it may look like, something is being done, but the work may be zero. Sometimes even you could have negative work. Although work is a scalar, it's not a vector. So you can't say that there is 30 joules of work in the north direction or something like that. It's just scalar, but it can certainly be positive and negative. So as you must be familiar with cosine theta, the value can go from +1 to -1. Okay, so depending on the angle, if the angle is such that cosine of that angle comes out to be negative, then the work will be negative. If the cosine turns out to be 0, then the work will be 0. For example, cosine of 90 is 0. So if you have a situation where the angle between the force and the displacement is 90 degrees, then 0 work is done. One example of this could be, for example, if a ball is being swung around in a circle like this. So this is the tension. Tension is the force, and this is the direction of the displacement. There is a 90-degree angle between them. So 0 work. Does that make sense?
Yep.
Yeah. So even though a force is being applied, things are moving, but still there could be 0 work. And thinking, more of an explanation or interpretation of this, this tension is not doing any work, is not doing anything to move this ball. The ball already had a velocity. You would have to have some other mechanism with which the ball was made to go in a circle. And then the job of this tension is only to keep it on the circular path, but it is not doing anything to move the ball faster or anything.
Okay.
Yeah, so that's why it's not doing any work. Um, Sometimes the work can be negative when the force is opposite to the displacement. And it's good that those of you who are in the lab section, you had done the lab with the planetary motion. There were some concepts related to this, which will make sense. That suppose there's a bowling ball which is moving with some velocity, and there's a big spring here, and the bowling ball hits this, right? And it will come to a stop. If you think about this, the spring will apply a force in this direction. Whereas for initial some time, the ball will keep moving to the right until it comes to a stop, right? So the direction of force and displacement are opposite. So in this case, the spring does negative work. And so it gains energy. So generally, if you kind of slow down something or stop something, then it is said to be negative work. And in that case, mostly this happens for mechanical systems that they can gain energy. So by doing
Okay.
work, the system gains energy. And then the opposite happens with positive work. If anything does positive work, then it loses energy. Um, Now imagine the same bowling ball. There's some other kind of arrangement going on here. Um, this has a velocity here, and there's some kind of a stretchy string that is attached to this. So as the bowling ball is moving this way, this elastic string is being attached, and so this force is being applied in this direction. So even though this force is not directly opposite, but it is kind of generally in the opposing direction, and its effect will be to slow down the bowling ball, right? So this will also do negative work. And if you think about it from this formula, W is equal to work is equal to FD cosine theta, you will have to use this angle. This angle is more than 90 degrees. Could be like 120 degrees or something like that. And if you're really, expert with your trigonometry, then you would know that cosine of an angle greater than 90 degrees is negative. So whatever is the tension here, whatever is that, let's say 10 newtons or something, and whatever is the displacement. But when you do cosine of 120 degrees, it will be a negative number, so it will make the whole work negative. Okay, so that's the idea of positive work, negative work. Questions?
I don't think so.
Okay. Then comes the idea of energy. Like I said, energy is the capacity to do work. Specifically, energy is divided into two types of energies. Kinetic energy and potential energy. So kinetic energy is defined as energy by virtue of motion. And potential energy is energy by virtue of position. So kinetic energy, whenever something is moving, it has energy stored in it. Again, if we think of the bowling ball, bowling ball is quite heavy. And when it's moving, it has energy stored in it. When it hits the bowling pins, it, it makes them fall. If the bowling ball hits something else, it could even break it, right? So there is a energy stored in it, and that is called kinetic energy. Again, the unit will be still joules, which is in short, it's written as J. Kinetic energy, there are a few different symbols used for kinetic energy. Sometimes it's Ke, sometimes it's just K. I like to use Ke for kinetic energy, and the formula is half mv squared. So if you know the object that is moving, if you know its mass and the velocity, then half mv squared gives you the kinetic energy. So suppose the bowling ball is 5 kg and it is moving with a speed of 6 meters per second. Then we would do half times 5 times 6 squared, which is 36. So that comes out to 90 joules. So that's how you calculate kinetic energy. Then there's potential energy. Potential energy is further subdivided into two kinds. One is gravitational potential energy. Its formula is mgh. And the second one is elastic potential energy. and its formula is half k x squared. Okay, so again, continuing with that idea of the bowling ball, if you take the bowling ball and if you put it at a high location, right, um, then it has a lot of energy stored in it because of being at a height. And so the kind of energy stored in that bowling ball due to being at height is gravitational potential energy. And if it falls from there, then it will release that potential energy, right? So let's take an example. Suppose the mass is 5 kgs, like I said, and G is gravity. Here, just for like simplicity, we'll round off the value of G to 10. Instead of saying 9.8, we'll make it 10. And suppose we have put it at a height of 8 meters. Okay, so that will be 400 joules. 400 joules is the amount of energy stored in it. Okay, then elastic potential energy. Elastic potential energy is stored in something that is elastic, like a spring. So suppose a spring gets compressed half. We need to know the spring constant. Let's say the spring constant is 200. Half times 200. X is the distance by which the spring is compressed. So let's say it got compressed by 10 centimeter, which would be 0.1 meters. So we will say 0.1 squared is 0.01. Actually, let me choose the K to be 2000 because 200 is a really small value for a spring constant. Okay, so half times 2000 times 0.01. So half times 2000 will be 1000, and 1000 times 0.01 will be 10. So that will be 10 joules. So that's how you calculate the potential energy. Then there is work kinetic energy theorem. It can be written as work done is equal to change in kinetic energy. What does that mean? Suppose you have a rocket and initially it is moving at, let's say it has a mass of 1000 kg. And initially it is moving at 10 meters per second. But then it fires its rockets and fires the propulsion rockets. And because of that, it generates a thrust. The thrust is um, 4,000 newtons. And it does that for a distance of 200 meters. Then what will be the final velocity is the question. So we will apply this principle. Work done is equal to change in kinetic energy. So let's first calculate the work done. That is easy. Work done is force times distance. So 4,000 times 200. So that's 800,000 joules is the work. Okay. This is also equal to the change in kinetic energy. So we can write it as delta KE. What was its initial kinetic energy? Initial kinetic energy is half mv squared, half times 1,000 times 10 squared. So that's 50,000. 50,000 joules was the initial kinetic energy, and the change in kinetic energy was 800,000 joules, right? So what will be the total? Uh, what will be the total kinetic energy, final? KE final is equal to 850,000 joules. And we will equate it to this formula, half mv squared. Half times the mass, which is 1,000, times the new velocity squared. We don't know what the new velocity is. We want to find that out. So we'll find it out this way. All right, so we'll solve for this. 850,000 is equal to 5,000 v squared. No, 500 v squared. So we will divide 850,000 by 500, and that will be equal to v squared. Then we take a square root of that. Comes out to be 41.23. This will be the final speed of the rocket. Questions about this?
I don't think so.
Okay. So that is work kinetic energy theorem.
Okay.
Then there is conservation of energy. So in situations where there is no friction and no new work is being done, then energy is conserved, which means that the total energy remains the same. So at any point of time, the total energy is sum of kinetic energy and potential energy. So we can write it as T1 is equal to T2. T stands for the total energy. In more detail, we can write it as KE1 plus PE1 is equal to KE2 plus PE2. All right. So at any point of time, a system has kinetic energy, some amount of kinetic energy, and some amount of potential energy. The sum of those should remain the same. So what's an example of this? Suppose we have an inclined plane, a smooth, frictionless inclined plane, and we have a block over here. This height is 5 meters. This is 10 kgs. And it starts from rest. Then the question is, what is the velocity at the bottom? So when you do these kinds of problems of conservation of energy, the things happening at the endpoints is what matters, not anything in the middle. So you have to choose the starting point and the end point, and you call them 1 and 2. All right. So you have to calculate the kinetic energy at 1 and potential energy at 1, and the kinetic energy at 2 and the potential energy at 2. When you're doing things like that, either you will calculate them as a number, or if it's unknown, then you simply write its formula. So what is the kinetic energy at 1? There is no kinetic energy at 1 because it is starting from rest.
Okay.
So 0. What is the potential energy? It is at a height. So it will have gravitational potential energy, which is mgh. Okay, mgh. So the mass is 10. G, we are just taking 10. And the height is 5. So that's for point 1. What is the kinetic energy at 2? Kinetic energy is calculated as half mv squared, but we don't know what the final velocity is. So we will have to write it as a formula, half. We do know the mass, so we can put that down. Half times 10, but the velocity is unknown, so we'll just call it v squared. And what is the potential energy at 2? The potential energy at 2 is 0 because the height is 0. So then this is it. We have to solve this to get a value for v. So this 0, 0, we can just get rid of them. And then we can cancel out the common things from both sides. So 10 divided by 2 will be 5. And there is a 5 on this left-hand side. So we can cross them out. And we are left with 10 squared is equal to v squared. So that was a very simple calculation. The answer is v is equal to 10. V is equal to 10 meters per second is the answer. This is a very simple calculation to demonstrate how this is done. It could be made into slightly more involved kind of problems, but this is the same principle that you use there.
Okay.
One more thing. The work done sometimes can be calculated using a graph by drawing a force versus distance graph or force versus displacement. So the displacement is on this side and the force is on this side. And when that happens, then the area under the curve tells you how much work is done. So you'll be asked to do that sometimes. So let me take a very simple example. Let's say this is the graph for the force versus distance. This is 10 newtons on the y-axis. This point is 10 newtons, and this is 1, 2, 3, 4. This is 4 meters. So the area made by the graph, or it's called area under the curve, is equal to the work. So if they ask you that this is the graph of force versus distance, what is the work done? Then you will calculate the area. Here, this will be very simple, 10 times 4, because this is a rectangle, right? 10 times 4 is 40 joules. So that's how it works, basically, in principle. Obviously, this could be made into more complicated situations. The graph could actually look like this. This point is 8 meters. So now this is a rectangle plus a triangle. So you just have to use your knowledge of geometry to calculate the area in parts and then add it up. And that would be the total work. All right. Questions?
I think I'm good.
Okay. So that's all about work and energy. And that will be enough for you to solve all the problems that are on this topic.
Okay.